So we would be talking about the error probability of the quadrature amplitude modulation in this video. So the system model that we have been using throughout is that as I of t is real part of AI some pulse shape g of t e to the power j 2 pi f ct. And in the last video, we defined quantity gamma s to be equals to Es over n naught. And before going on to finding the what is error probability for the quadrature amplitude modulation or QAM, we would first see what is the relation between Es over n naught with the signal to noise ratio. So if you want to compute what is signal to noise ratio, so it would be equals to the received signal power divided by the noise power. That's how you would define a signal to noise ratio. So if I call signal to noise ratio SNR, then SNR would be equals to the received signal to noise ratio, which you can write as the symbol energy transmitted divided by the symbol interval, right? So that would be your power, the received power in the absence of any attenuation, and divided by the noise power, which would be equals to N naught B. So that would be your signal to noise ratio. Now, if your bandwidth and the symbol interval product B times Ts, if that is equals to 1, in other words, your bandwidth is nothing but 1 over Ts, then your signal to noise ratio would be equals to Es over N naught. So Es over N naught is really something that is related to the signal to noise ratio, and we have been calling it to gamma s, which is somehow used as sometimes as a symbol of the signal to noise ratio. So your gamma s would be your signal to noise ratio if your bandwidth time a symbol interval product is equals to 1. In other words, if your bandwidth is reciprocal of your symbol interval, then Es over N naught would be equals to your signal to noise ratio. So now we have once we have talked about the relation between Es over N naught and signal to noise ratio. Now let's talk about what would be the error probability for the quadrature amplitude modulation. And we said that for the sake of simplicity here, we would restrict ourselves to be square constellations. So we would say that, for example, if M is a square constellation, that means it would have the number of symbols to be transmitted would be a perfect square. So let's call it a L square. So for example, if M is equals to 4, that would be equals to 2 square, and capital L would be equals to 2 in that case. So if we have M is equals to 4, and if you want to draw a constellation of a quadrature amplitude modulation, remember both your uh, amplitude as well as the phase would change here. So this would be something like your constellation diagram. So if you call it this S1, if you call this constellation point to be S2, this constellation point to be S3, this constellation point to be S4, and then you can compute what is the minimum distance between different constellation points. For example, S1 and S2, if you want to compute what is the minimum distance between these constellation points, you can project these constellation points onto the basis function phi1 of t, and let me call it S11, and that would be called S21. And the distance between these two constellation points, you can see, is the distance between these projection in this particular case. So if I want to compute what is D12, for example, or square of that, that would be equals to S11 minus S21 whole squared minus plus S12 minus S22 whole squared. In other words, the projection of the constellation point S1 onto the basis function phi1 would be S11, and the projection of the constellation point S2 onto the basis function phi1 would be S21. You take the difference in the square, that would be your 1 point, that would be part of the distance squared, and then you have to project both of these onto the other basis function. S12 would be the projection of S1 onto the basis function phi2, and S22 would be the projection of the constellation point S2 onto the basis function phi2. So this would be S12 and this would be S22, and you can see both of these are equal, and if you subtract them, that would turn out to be 0. So that goes away, and hence your distance is simply S11 minus S21 squared. So your d min would, in this case, would be equals to 2d. And you can see that this is similar to a minimum distance that you got um, in your pulse amplitude modulation. So your minimum distance in this case turns out to be 2d, and it is similar to the pulse amplitude modulation. If I call AI to be equals to 2i minus 1 minus L times d, where you know that L is nothing but root of m. So on this axis, if you have a square constellation of m points, and if you project on phi1 of t, you would have capital L number of projections onto the basis function phi1, where the distance between the minimum distance between those 2 points would be given by 2d, where where or the distance of the amplitude of each of those constellation points projected onto the basis function phi1 would be given by ai minus 1 minus L times d, and you would have capital N number of points on this axis. Similarly, you can project your constellation points onto the basis function phi2, and you would have a similar equation for the um, uh, for the constellation point projection projected on the phi2. Hence, you can think of the constellation of a quadrature amplitude modulation as two branch constellations. So, as two constellations to 1D constellation, which are nothing but the projection of the constellation points onto the basis function. So rather than one 2D constellation point, you can think of as a two branches, and each branch is a one-dimensional constellation point. And then you can compute what is called the symbol error probability of a branch. So if you want to compute that, so symbol error probability of a branch, let me call it. Remember what was the symbol error probability um, for the pulse amplitude modulation. So for the pulse amplitude modulation, you had 2 into m minus 1 over m q function of root 6 gamma s bar over m minus 1. That was the symbol error probability for pulse amplitude modulation, Emery pulse amplitude modulation. But now you have two branches, and each of the branch would get equal amount of power, that would be equals to es bar by 2. So in this case, your symbol error probability would change. How? So your symbol error probability in this case would be equals to 2 times root m minus 1 over root m times q function of root 3 gamma s bar over root m minus 1. That would be your so that was m square minus 1 here. So that would be m minus 1 here inside. So that would be your symbol error probability of one of the branches for the quadrature amplitude modulation. And now if you want to compute what is the total error probability, then you can think of this as what would be the probability of the correct detection in one of the branch. So the probability of the correct detection that would be equals to 1 minus the probability of a error in a branch. So that would be probability of the correct detection in one of the branches, but you have two branches. So you can assume that both of these branches would have a probability that is independent to each other. So the probability of the correct detection overall would be square of this quantity. You would have this as a probability of the correct detection for both the branches now. And now if you want to compute what is the symbol error probability, that would be simply equals to 1 minus the symbol error probability of a branch whole squared. So that would give you the overall symbol error probability of the quadrature amplitude modulation. In other words, your overall symbol error probability can be written as PS would be equals to 1 minus 1 minus 2 times root m minus 1 over root m q function of root 3 gamma s bar over m minus 1 whole squared. So this would be your symbol error probability, which is nothing but 1 minus the probability of the correct detection of the both of the branches, because this is nothing but the probability of the correct detection of one branch. Square of that would be the probability of the correct detection for both of the branches. 1 minus that would give you the symbol error probability. And again, if you have gray coded your signal, then your bit error probability would be nothing but your symbol error probability divided by log base 2 of n. Please note that in these videos, I have used PS and PE to be synonyms. That is, both of these quantities uh, denote the symbol error probability in a particular context. But there are other, what about, this was for rectangular constellations, but what about, this was about square constellation, but what about rectangular constellations? So if you have non-square constellations, so typically what people use are bounds, and they say the symbol error probability would be less than or equals to 1 minus 2 times q function of root 3 gamma s bar over m minus 1 whole squared. And typically they also say that this would be less than or equals to 4 times q function of root 3 gamma s bar over m minus 1. Um, so another way of writing the symbol error probability is that you write uh, md min, where your md min is the largest number of nearest neighbors, number of nearest neighbors, times q function of d min over root 2 and naught. This is also used in some places. So that is what we want to talk about, the error probability equations for the linear modulation schemes. Another modulation scheme that we want to discuss here is what is called the differential phase shift keying. The differential phase shift keying, that is very useful because that does not require synchronization at the receiver end, because uh, your reference is transmitted with your signal, that is your previous symbol acts as the reference for the current symbol. That means if you have, for example, a bit sequence here, so the information is encoded into the transition, so what we call it the phase transition. For example, if you have this sequence as 0, 0, 0, 1, 1 0 and 1 1, and then for a 0 0 you would have a phase transition of a 0, and then for example you have a phase transition of pi by 2 for a 0 1, and then for a minus pi by 2 for a 1 0, and then you have a phase transition of pi um, for a um, bit sequence of 1 1. So this is how you encode your information. That means you look at what phase was transmitted in the previous symbol, and whether or not you have any phase transition in the current symbol. And if you don't have a phase transition, you decode the information as 0 0. If you have a transition of 0 1, you say that 0 1 was transmitted. So you, of course, you need a phase comparator or devices of that sort in order to uh, decode that information. So, but the important thing here is the error probability equation for MRE differential phase shift keying is pretty difficult. But fortunately, for a binary differential phase shift keying, which is also called DBPSK or DPSK in short, so differential phase shift keying in short without any M would be called as a binary phase shift keying. And the error probability equation for a binary phase shift keying turns out to be a very simple equation in terms of signal to noise ratio or ES over N naught. It turns out to be that the error probability equation for a differential phase shifting is 1/2 e to the power minus gamma b. It's a really simple error probability equation, and we would make use of that with so how would a differential phase shift keying, for example, a binary differential phase shift keying would perform under fading when we talk about the performance under fading. This, remember, for all of these modulation schemes is the performance under the AWGN channel, and this would change as we would move from an AWGN channel to the wireless channel. Um, Please note that for a differential phase shift keying, you would always have a 3 dB penalty. If, for example, this is the performance with BPSK, you would get 3 dB worse performance with differential phase shift keying. It would be DPSK, and that was BPSK, where on this axis you have your signal to noise ratio, and on this axis you have your error probability. In this case, the symbol error probability would be equal to the bit error probability. So these are one of the same thing. You would always get a 3 dB penalty. So you have to transmit 3 dB more power in order to get the same error probability with DPSK as compared to the BPSK. So that is one point. So, as a summary point, as a last concluding point, we can say that for these linear modulation schemes, your symbol error probability as a function of the gamma s can be approximated as, if PS is your symbol error probability, you can say that it's approximately equal to some constant alpha m q function of root some constant beta m times gamma s, where this alpha m and beta m are the constant that would depend on the modulation type. So alpha m, beta m would depend on the modulation type. But you can take this symbol error probability to do the generic analysis. For example, if you want to carry out a generic analysis, you can assume that your symbol error probability is alpha m q function of root beta m gamma s. From that you can compute carry out the generic analysis. So we would stop here. That would conclude the topic of the performance of the digital modulation scheme under the AWGN channel. And in the next lecture, we would start talking about the performance under fading, which is the topic of the day. And that we will talk about in the next video.